Hello everyone, my name is Tai, and in this term project video for Math 233 or Calculus 3, I'm going to explain to you all more about chapter 14.3, which is partial derivative. So let's proceed to the presentation. So as I have mentioned it earlier, I'm going to go through chapter 14.3, which is partial derivative. In this presentation, I'm going to go through these main points, which are partial derivative of function of two variables, as well as function of more than two variables, partial derivative and continuity, second order partial derivative, the mixed derivative theorem, partial derivative of still higher order, and differentiability, as well as at the end of this, I'm going to solve some exercise from the chapter. So this first main point, which is partial derivative of a function of two variables. This is the definition of partial derivative of f of x and y with respect to x at point x sub 0, y sub 0, which is equal to limit as h approaches 0 of f of x sub 0 plus h and y sub 0 minus f of x sub 0, y sub 0 over h. And this is the definition of partial derivative of f of x and y with respect to y at point x sub 0, y sub 0, which is equal to limit as h approaches 0 of function f of x sub 0 plus h and y sub 0 minus f of x sub 0, y sub 0 over h. In this next point, which is function of more than two variables, as we all know, the partial derivative of a function of more than two variables are the same as the partial derivative of function of two variables, where we do the derivative with respect to one variable while keeping others as independent variables. Move on to the next point, which is partial derivative and continuity. As a function of f of x and y can have partial derivative with respect to both x and y at a point without the function being continuous at that point. This is different from a function of a single variable where the existence of derivative implies that there is continuity. If the partial derivative of a function of f of x and y exists and are continuous throughout this center at x sub 0, y sub 0, then f is continuous at that point. Continue to the next point, which is second order partial derivative. When we differentiate a function f of x and y twice, we produce its second order derivative, as example shown below in this presentation slide, such as f of fxx, fyy, fxy, fyx. Move on, the mixed derivative theorem. So in this theorem states that if a function f of x and y and its partial derivatives fx, fy, fxy, and fyx are defined throughout an open region containing a point a, b, and are all continuous at a, b, then fxy at point a, b and equals to fyx at point a, b as well. This next point, which is partial derivative of still higher orders, we can differentiate the function as many times as we want, as long as there is derivative. Then we can get this kind of derivative with higher order, such as third order or fourth order, like the example shown below. In this next point, which is differentiability, which is mostly a theorem, I'm going to show you all these. For the first one, which is function of a single variable, that if y equals to f of x is differentiable at x equal to x sub 0, then the change in value of f that result from changing x from x sub 0 to x sub 0 plus delta x is given by the equation of the form delta y equals to f prime of x sub 0 delta x plus epsilon delta x, in which epsilon approaches 0 as delta x approaches 0. This next theorem, which is the increment theorem for the function of two variables, states that suppose that the first partial derivative of f of x and y are defined throughout an open region R contain the point x sub 0, y sub 0, and that fx and fy are continuous at x sub 0, y sub 0, then the chain is delta z equal to f of x0, fx sub 0 plus delta x, and y sub 0 plus delta y, minus f of x sub 0, y sub 0. In the value of f that results from moving from x sub 0, y sub 0 to another point, x sub 0 plus delta x, and y sub 0 plus delta y. In all, satisfy the equation of the form delta z equals to fx of x sub 0, y sub 0 plus delta x plus fy of x sub 0, y sub 0, delta y plus epsilon 1, epsilon sub 1, delta x plus epsilon sub 2, delta y, in which each of epsilon sub 1, epsilon sub 2 approaches 0 as both delta x and delta y approaches 0. Moreover, a function z equals to f of x and y is differentiable at x sub 0, y sub 0 if fx of x sub 0, y sub 0 and fy of x0, y sub 0 exists, and delta z satisfies an equation on the equation below, in which each of epsilon sub 1 and epsilon sub 2 approaches 0 as well as both of delta x and delta y approaches 0. We call f differentiable if it is differentiable at every point in its domain and says that its graph is a smooth surface. In this, if the partial derivative fx and fy of a function fxy are continuous through an open region R, then f is differentiable at every point of R. And in this last point, which is differentiability implies continuity, if a function f of x and y is differentiable at x sub 0, y sub 0, then y is continuous at x sub 0, y sub 0. So now, as I have explained all of the parts in the chapter 14.3, I'm going to solve some exercise from chapter to give you a better understanding of this chapter. So let's move on to the first exercise, which is to find all the second order partial derivative of the function below, f of x and y equal to sine xy. So in order to do this, we first have to find the first order partial derivative of the function with respect to each variable, which we got fx equals to y cosine xy and fy equals to x cosine xy. And finally, we can find all the second order partial derivative of the function. Fxx is equal to negative y squared sine xy, and fyy is equal to negative x squared sine xy. And the next one, as we all know that the mixed derivative theorem states that fxy is equal to fyx. So we got the same answer, which is cosine xy minus xy sine xy. And that is the answer. Moving on to the next exercise, number 2. So in this one, we have to use the partial derivative to find partial derivative of the function f with respect to y at point negative 1, 0, 3 for the function of x, y, and z equal to negative 2 x y squared plus y z squared. So first we need to write the definition of the partial derivative, which is equal to the limit as h approaches 0 of f of x sub 0 plus y sub 0 plus h and z sub 0 minus f of x sub 0, y sub 0, z sub 0 over h. And then we need to input all those points into the equation, where we got a limit as h approaches 0 of x of f of negative 1, h and 3 minus f of negative 1 over 3 over h. And then we got the limit as a approaches 0 of 2h squared plus 9h over h. And then we got limit as h approaches 0 of 2h plus 9, which equals to 9. And that's the answer. Move on to our last exercise, which is to find the value of of partial derivative of z respect to x at the point 1, 1, 1 for the equation xy plus c cubed x minus 2yz equal to 0. So in this, first you need to find the partial derivative of f respect to x and z. So we have the function f of xyz equal to f, so equal to xy plus z cubed x minus 2yz. So we can find the partial derivative respect to each variable, which is fx, which is equal to y plus z cubed, and respect to z, which is equal to 3z squared x minus 2y. So in order to find the value of partial derivative of z respect to x at point 1, 1, we know we need to use the equation below, which is equal to negative partial derivative of x of y respect to x over partial derivative of y respect to z, which is equal to negative of y plus z cubed over 3z squared x minus 2y. And then we need to insert those point value, which is at 1, 1, 1, and then got the answer of negative 2. So this is the end of my presentation. I hope you have a better understanding of this chapter. And if you have any other question, you can ask me later on. So I want to say thank you so much for your time, and I hope to see you soon in my next video.